All right, today we're going to do just some quick practice problems. We have our test this week, so we're going to work on if you don't know what gas law you're working with, how to figure that out, and then just some quick practice, like I said. So the first one, there are 135 liters of gas in a container at a temperature of 260 degrees Celsius. If the gas was cooled until the volume decreased to 75 liters, what would the temperature of the gas be in degrees Celsius? So the first thing I want to point out is even if they ask for the temperature in degrees Celsius, you need to know that you cannot leave it in Celsius. With all of the gas laws, every time you see it in Celsius, you have to train yourself to convert it to Kelvin. And in this class, we're okay with just adding 273 to get it from degrees Celsius to Kelvin. Then we'll work our magic, and then if they want it in degrees Celsius at the end, we will subtract 273 at the end again. So back to figuring out what gas law to use. They give us a volume at the beginning, and they mention temperature. They mention volume again, and they mention temperature again. So we're going to be using Charles' law. So that means we have volume and temperature. So V1 and T1, V2, T2. Let's set up a table to keep us honest here. We have an initial condition, volume 135 liters, temperature 260 degrees Celsius, volume decreased to 75 liters. Temperature is what they're asking us to find. Remember, we are converting to Kelvin from our temperature. Adding 273 gives us a temperature of 533 Kelvin. Charles' law states V1 over T1 equals V2 over T2. That is a direct relationship. Since our volume is going down, we should expect our temperature also to go down. When we plug in our values for volume and temperature in here, we get V1 is 135 liters over T1, 533K, equals V2, 75 liters, that was a liter, over T2, which is solving for. We cross multiply our 533 times 75, divide by the 135, and we get T2 equal to 296 Kelvin. Problem is they want it in Celsius. We have to now subtract back out our 273 and get our final answer to 23 degrees Celsius. All right, our next question is a 35-liter tank of oxygen is at 315 K. Notice it's already in Kelvin, so that's good. With an internal pressure of 1.90 atmospheres. How many moles of gas does the tank contain? And they give us a value of R. So right away, I notice they mention moles. And when they do that, they're giving us the amount of the gas, which is a good thing. They're giving us a V, they're giving us a T, they're giving us a pressure, and they're mentioning moles, and they're giving us the R value. So I know that this is a problem where I'm going to be dealing with the ideal gas law. V is 35 liters. P is 1.90 atmospheres. N is what they're asking for. R, they've given us 0.0821 liters times atmospheres over moles times K, which I know is a large unit, but it's what relates all of the rest of the units together. And our temperature is 315 K. All of our units should match the unit that's in Kelvin, or I'm sorry, in our R right here. So are our units for volume liters? Yes. So that's good. Pressure atmospheres? Yes. Temperature Kelvin? Yes. And so when we get N, it should be coming out in moles. So that's good. Let's go ahead and plug and chug. PV equals nRT. Plugging in for P, 1.90 atmospheres. V, 35 liters, equals N. R, we'll just put 0.0821. And T, we're putting in 315 K. Now, to solve for N, we want to multiply the 1.90 times the 35, and then we're going to divide by both the 0.0821, and we're going to divide by the 315 because we have to get both of those on the other side. When we do that, we get an answer of 2.57 moles. So make sure that when you do this problem that you get that answer. All right, next on the agenda. I know we're going fast, but this is a review. We've done these before. Number 3, a gas is 67 liters is reduced to 44 liters. So that means we have a V1 and a V2. If the original pressure, so that's P1, was 330 torr, what's the new pressure? So that's the P2. So we have P1, V1, P2, and V2. So this is Boyle's law. P1 is 67 liters. I'm sorry. My bad. P1, the original pressure, is 330 torr. V1 is 67 liters. P2 is what they're asking us to find, and V2 is 44 liters. Now, mind you, this is an inverse relationship between pressure and volume. So if if volume goes down, we should see pressure go up. So just always check yourself. Boyle's law is P1 V1 equals P2 V2. P1 is 330 torr. V1 is 67 liters. P2 is what we're solving for, and V2 is 44 liters. We're going to multiply the 330 times the 67, and then we're going to divide by the 44, and we should get an answer of P2 equals 503 torr for our final answer. And we said that it would go up from 330 torr, so we should be right there. Finally, number 4, a gas with a pressure, so we have a P of 255 kPa, kilopascals, and at a temperature, so we have a T of 125 degrees Celsius, is lowered to a new temperature, so we have another T, so we have a T1 and a T2. What is the new pressure? So we got a P1 and a P2. This is Gay-Lussac's law, also called Amonton's law. Depends on what textbook and who you're following. So we have P1 is 255 kilopascals. T1 is 125 degrees Celsius. P2 is what we're looking to find, and T2 is 74 degrees Celsius. Quick check of units tells me my degrees Celsius have to be converted. We have to add 273. That gives me 398 and 347. So because pressure and temperature are directly related, temperature is lowered, that means pressure should also be lowered. So if it was 255, it should be lower than that once we're done. So let's double check that. Our equation is P1 over T1 equals P2 over T2. Plugging in a chugging, we get 255 kPa over 398 kPa. Oh, I'm sorry, 398 K lots of K's going on there, equals P2 over 347K. Solving for P2, we get 222 kPa. And we said if temperature was lowered, pressure would also be lowered, and it was 255, and it went down to 222. All right, so always double check your units. Remember, volume units can be anything except when they are in the ideal gas law. They have to be liters. Temperature units always have to be in Kelvin. Pressure units can be anything except when, as long as they're consistent, except when you're in the ideal gas law, you have to make sure they match the R value. If the R value is atmospheres, you got to use the 0.0821 value, and then have the pressure be in atmospheres. If it's in the 8.31, it's in kPa. Just pay attention to what is given in the problem. Try and label everything and find your variables.